Today we're going to talk about meshes and smoothness. Can you guys see my screen okay? Um, okay, so meshes are a pretty common thing in digital workflows, but not everyone uses them, and I want you to understand what they are and sort of understand their use and when to use them versus like surfaces and NURBs and things like that we've basically gone over before. So we'll go over creating simple meshes from scratch, creating meshes based on surfaces, topology, and mesh subdivision and smoothing. So let's talk about what a mesh is. Does anybody use meshes when they model in Rhino? Okay. Um, does anybody know like why? Like, what they're good for? Just to understand what you guys understand. No. Um. Well, it's meshes aren't like surfaces, but they're a little like surfaces in the sense that they are used to describe shapes, right? So but they can do that with just polygons. So where a surface would be sort of one sort of geometric entity, a mesh is sort of made up of a bunch of individual sort of polygon shapes that combine into some sort of like larger form. So where a surface is inherently smooth because it has sort of like NURBS, curvature, and things like that. Um, a mesh isn't. A mesh is made out of triangles or quads or even more they call n-gons, any number of sided polygons that go together. And so smoothness is usually achieved through um, the number of polygons that you have, and through visualization using the graphics card to take the planar or non-planar surfaces and generally give them a smoothness. And so, like I said, they're made out of triangular faces, quad faces, polygonal faces, or other mixtures of things. Um, and they can be used to represent fairly detailed geometries. This is the Sanford bunny, which is a standard um, standard mesh, free mesh that was a scanned object that a lot of people use because it's free to use, sort of copyright free. So you'll see a lot of Stanford Bunny things in graphic design for testing. And so you can have the triangular meshes and the quad meshes, and you can see that the quad mesh looks fairly smooth, but it's actually still made out of just like 4-point surfaces that are put together. The smoothness on the surface is deceiving because that's a graphic trick that smooths the eye or the light that's reflecting off of these. If you look at the edge, it's still straight segments that's making that up. Um, and so what the computer does is it uses a shading algorithm that can be applied to the mesh so that it appears to be smooth when it's displayed or rendered. Um, and so that's what sort of takes these essentially a low poly model and makes them smooth. That's what happens in graphics and video games and movies. A lot of times is they'll put they'll put a shader on the object to smooth it out so it looks more curved than it is, but the geometry is actually super lightweight. And so as opposed to a surface that might take on this form, um, the the mesh is really only made up of points and faces. And so it's storing very little information in the computer, and therefore the computer can use them very quickly. So let's talk about meshes in computational design. So, like I was just saying, meshes are used in computational design because they can be used to describe any sort of complex geometries, but they also store other sort of information about that geometry. So their vertices and mesh faces sort of make up a topology on how things are connected. And so we can use that information to get more information out, or to know sort of what things are next to each other. And so that also helps us determine things like the direction of the mesh and the normal of the mesh, and it makes them really useful for controlling as control geometry. So for an example, there's a pavilion by the ICD and the ICKE that they generated some control sort of polygon mesh, which represents the geometry that they were making in a very low poly manner. But because this mesh sort of had embedded logics of what face was next to what face, and what vertices were connected to what vertices, you could use that to then build other geometry on it. So they could say, if they wanted to make a component type system, and a lot of you that posted the computational facade examples use examples that share the same sort of logic, where they had an underlying surface. And my mic is lagging a little bit. Let me know if that continues. So they had this underlying mesh, and they could build some sort of topological model on that, and so they knew what shared edges were, and then they could build more complex geometry from that as a framework, basically. Through the mesh, they could generate sort of surface normals, they could get shared edges, they could generate this geometry, and then when they were changing the form, they could basically work with simple geometry to make more complex geometry happen. So it's a good sort of setup. Similar to how control points are adjusting the surface, a mesh can be used to adjust more complex design geometry. So that's really helpful in some cases. And then, as Kinsey pointed out, for extreme complex systems, meshes are actually really the only way the computer can handle things. So in landscape architecture, where they have really complex, excuse me, large surfaces, sites that might be, miles long, or huge regions, then a mesh is really the only way to store that information, because it has to be light enough that all of it can be put in, and a surface would just bog the computer down. So keep that in mind. If you have very complex models, or if you need to represent a lot of form, the best way to do it is to use a mesh. Okay, so let's talk a little bit about meshes in Rhino. So there are a lot of different ways of using meshes. Rhino just uses one of them, and that's basically where Rhino contains a list of vertices and then a separate list of mesh faces. And so that's either the 3 or the 4 integers, which are the indices in that list of vertices that represent the connectivity of that face. And then this also, depending on the order that you're selecting those faces or those vertices, the face will point one direction or the other. So here's an example. So on the left, you have a list of vertices. You know, the vertex array that represents these points: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 through 15. All in one sort of list. Nothing but their order and point location in that list. And then there's a separate list that talks about what order that you connect these. And so in the case of Rhino, the sort of standard way of doing this is going to be counterclockwise. So if you take your right hand and sort of make a counterclockwise motion from the order that you put the points, your thumb is going to be the vertical or the normal direction to that mesh face. So in this case, where we have the face labeled H, you have 9, 10, 14, 13. 9, 10, 14, 13 is in a clockwise direction. And so that normal is going to point out towards us in that direction. We see that I is the other direction. It's 11, 10, 14, 15, which means unlike a surface, a mesh can have multiple directions. One face can point one direction and one face can point the other direction. So that one can actually point inside, since these are all sort of individually determined by this list. So that can be problematic, and usually as you typically don't want to switch directions of the faces in the middle of a mesh. So we'll stick to the convention that you're always using, you know, counterclockwise direction. And so that's a very efficient way of storing geometry, because there's really just two lists of information, and only one list shows the geometry, and the other one represents the topology, right? So let's talk a little bit about geometry versus topology. So we have these 4 objects here. When we look at geometry, 3 of the objects have the same geometry. A, B, and C are exactly the same form. They're all these cube type forms. One is a quad mesh with 6 sides. The other 2 are triangular meshes with 12 sides. Now the 4th one, or actually all 4 models have 8 vertices, right? 4 on the top, 4 on the bottom. So when you're looking at this information in, you know, the information that's stored in the mesh, the vertice list is all going to be the same. But the topology list is going to be really different. Well, the length of vertices of these 3 and this one is all going to be the same, but the point locations are going to be different. The topology is going to be different from this one to this one to this one. So you can see here that the mesh face triangle is connecting these points, and this one's connecting these points together. Now the topology of C and D are exactly the same. The same points are connected in the same order, getting the same triangular faces, but the point locations are different. And this is almost what B is. It's really difficult to distinguish the topology difference in this one and this one. There's actually only one side of this shape that is different. You can tell in the bottom, if I rotate it this way, it looks a lot like this one. And if I rotate this top one this way, it looks a lot like this one, except this bottom face is connected in this direction like C is instead of like B is. So the topology is super, super similar. It's exactly the same as C and D, but C and B are slightly different, and A is really a different topology than all of them because it's a quad mesh. So it's important to note when you're making these meshes topology is a really important factor for meshes because it allows for a lot of things to happen. We want really clean meshes with very clean topology, and we'll show examples of topology that's not very clean. And there's a couple things that meshes don't like. So say I had these 8 points in space, I can create this outside mesh in any case. I can also create mesh faces that connect inside, where in this case, every edge in every case is shared by 2 faces. In that case, if you connected a point from this corner to this corner to this corner, you would have a mesh face that follows the same sort of rules as the other faces. It's, counterclockwise in the list and connected to the same number of points, but it would cause this edge to share 3 faces. Now that's called a non-manifold mesh, which means if you were to splay it out, you would have, say, 2 faces that go out and 1 face that goes in. So topology-wise, meshes don't like that. It's still possible and you can do that, but topology-wise, it's not so good. It makes it a little dirty. Now you can also have one of these, if you took away, say, the tops of all of these, you can have other types of edges. So an edge that has 2 faces is considered clothed. It's sort of covered on both sides. If you took off this top and just had this single face, you'd have what you call a naked edge. It only has 1 face that it's adjacent to. The same with vertices. A vertice in the middle would have these four faces. It can have more or less than that. But if it's not completely surrounded by faces, then it's considered a naked vertice as well. And that can be useful in a lot of cases. And we'll see that, I think, on Wednesday when we're starting to look at physical simulation of stuff. Okay, so let's create an example from scratch. And how would we do that? And this is it's rare that you make a mesh from scratch, but I want you to understand how you do it. So say we want to make this little pyramid type shape, triangular pyramid. We're going to have a set of points, 0, 1, 2, and 3. And we're going to use those points to create mesh faces between them, specifically in a counterclockwise direction. So if you look, I've made a script that does that separates the different faces out. And what we're actually providing this mesh constructor is faces that represent the number or the indice of the points that are in this. And so that first mesh face is going to be 0, 1, 3. So if you connect 0, 1, 3, it's going to make this front face right here. Right? Now the next one is 1, 2, 3. So you have 1, 2, 3. It's going to connect this side. Then you have 2, 0, 3 is going to connect the back side, facing away from us, right? Now 0, 023 and 101 should have the same sort of topology. We're actually, sorry, 203 should have the same sort of topology because it's counterclockwise when you're looking at it from the back side. So the normals of those surfaces will still sort of face out. And then you have the bottom edge, which is 0, 2, 1. So it would face down. So let's do an example of that. We can quickly sort of model it. In perspective, I'm going to add a couple points. Add these somewhere in the middle. And move it up. So if I add these multiple points, I want to make sure I know the order of them. Very specifically. So I can say point list, give it a larger number so you can see it. Okay, so this is the basis for our mesh. So under mesh, also turn on my bifocals. Am I still lagging, by the way? Sorry. Okay. So if I wanted to connect these into a mesh, I need a construct mesh component, which takes in the vertices list and the face list and colors optionally if you want to do that. And I'm going to face. Get a mesh triangle. Okay. So we have the vertices that are going into that, and it'll automatically try to make something from whatever topology you have, and you can see it's not doing a very good job of it. It has 4 points, so it tries to put it into a quad. But we're gonna set up the topology that we had in this case. Okay. So what we need is to say what numbers are important for this. So I'm going to say a number slider 0 to 3. So my first face is going to go A, B, and C. And this is going to be 0, 1, and 3. Now if I plug this into the face, it should automatically connect those into a mesh. I'm going to copy those. It's going to go 1, 2, 3. Plug those in the right order. It's that face. And 2, 0, 3. And 0, 2, 1. perfect. We have our 4 sides. And you can see this is about as simple a mesh as we can make, and that was already like super tedious to just do, like plugging in each point for each mesh face. Kind of takes too much time. But to construct it from scratch, if you wanted to do that, that's kind of what you would do. Okay, so let's look at making a quad. So a quad's a little easier because with the 4 points, you would only have one mesh face. You could potentially describe a closed one if you sort of gave different topologies. But that's a little bit easier, and so instead of using this triangular face, we can use a quad mesh. 0, 1. Let's make those. So it's making what it was doing before, and you can see that it connects all the points together, but that's definitely not a planar surface or a planar mesh. It's sort of bending around this little lower edge. So it's important to note triangles are always planar. So a triangular mesh, all the faces are going to be planar polygons. In most cases, quad meshes will not be planar. There are special cases that are planar quad meshes that can be made. That's usually more regular geometry, like a sphere or some revolved solid that can be broken up into a planar mesh automatically. There are ways of taking a mesh with non-planar faces and trying to optimize it so everything becomes planar, and that's pretty useful. Say if you're doing a facade system where you had a lot of planar non-planar faces and you want to optimize it so that you can make things out of, say, flat stock like sheet metal or wood or something like that. But usually when you're making them on complex geometry, they will not be a planar mesh. Okay, so let's continue with this. So we can make triangular and quad meshes from scratch. But that's kind of tedious. So there's other ways that, especially when you have these complex meshes, you know, if we wanted to go through and make the Stanford Bunny mesh from scratch, that would be so many mesh faces, it would be ridiculous and not be worth the time to do that. So we have other ways that we can do things. One is through triangulation. So if you have a set of random points, or they don't necessarily have to be random, they can be ordered, but you want to make a simple mesh from it. There's a lot of tools to be able to do that. One of them is called a Delaunay mesh. And so what that is, and you can see an example of this, is all of these points are just sort of like random in a rectangle. So a populate 2D space gives you a random set of points. Now let's go ahead and do that so we can visualize that a little bit better. So if I randomly populate a set of points, I did 3D, 2D, so it's flat, and I wanted to make a mesh on that. Now, I don't know the order of these points. They're probably all over the place, so it would be difficult to make my own sort of topology for that. What the Delaunay mesh does is it takes these points and a plane in which it's working with. That helps that all of these are planar because it can project down onto that its algorithm that makes that work. And so what that is it'll take all of these points and it'll find 3 of them. And if it can connect a circle around those 3 and not include any other points, then it'll make a mesh face. And so those are not super nice triangles. They're all over the place, but it simplifies the process so you don't have things crossing over each other and sort of internal mesh faces and things like that. So let's see if we can look at that more specifically. So if you have this mesh, and say I explode it. Exploding a mesh will give you all the mesh faces as separate individual meshes. So you see that these are all triangle faces where I have 3 vertices in one face. Let's turn off some of these. And if I just select one of them, I'm going to get an list item. And we have 185 of them. So this should give me one of those. And you see the ones on the edge are really long and stretched out. So if I say up here there's a tool, I think under analysis, that you can get face circles. So let's look at what that face is. Why do you get those long stretched out ones? Well, because I can connect these 3 points and not include any other points in there. And so that only works around the edge, because anywhere else you would have a lot of points. So if I select another one in the middle somewhere, you can see that the circle that this is creating, there's no other vertices except for those 3 that are in there. Now, if you were to cut this mesh, these 2 mesh faces the opposite way, instead of connecting from here to here, if you connect it from here to here, then these 3 points would create a circle that's much larger and would include multiple other vertices. So that's why it's a useful sort of algorithm, because it makes as close to regular triangles as possible. Instead of stretching them out, it minimizes the interior angles of that triangle. So typically if you do something like that, you only have to worry about the edge sort of conditions where they stretch out and get long. But that's useful, and we can use that in any number of ways. So let's see how you might use that on a non-planar surface. So you have say you have this complex sort of surface. And that's something that you can just model. The underlying geometry underneath this is a simple sort of surface where you rebuild it and pull the points around. You can also in the example files just copy that over if you want to use the exact same surface. So I'm going to turn this one off. And I just copy this surface over so we have some sort of consistent starting surface. Let's hide these things. So we can make meshes on this surface in any number of ways. If we wanted to use say a daylight name mesh to somehow generate topology across this surface that was more regular as opposed to sort of stretched out, we might start with points that are more regular. So we can use some of our, say, lunchbox tools. Right now, I'll pick like a triangular panel, and I'll set some number of panels. Some number of panels in both directions. So 12 and 12. So we have a regular sort of surface network, not a mesh network, but surface network. It looks a lot like a mesh because these are individual polygons, but this is multiple surfaces. And if we wanted to make meshes out of those, we could. Now there's simple ways to make meshes. Since these are all individual surfaces, you could potentially say a really good tool for making simple meshes is called Simple Mesh, and it'll take these and make it as simple as possible. Now that will turn all of those surfaces into individual mesh faces. That's useful. Now, if we plugged it into the surface itself, it simplifies it a little too much. It just makes it a quad again. We can plug any sort of geometry into just a mesh container, like any kind of surface geometry, and it'll try to mesh that. But you can see that it does a pretty horrible job topologically of making this a consistent mesh. So we don't want to do that. And if we want to have more control over these panels, let's sort of continue how we were going. So we want to somehow take each one of these panels, and we'll use that as a framework for creating more complex geometry, similar to what we were doing in or the computational version of it that we were looking at with the provider. So we're gonna take each one of these mesh faces. Let's find the center point of that. We can do that by looking at the area of that panel, and that'll give us that center point. Now, if we wanted to make that triangular pyramid that we were doing before, when I made those 4 points, I made the 3 base points, and then I moved the middle one up vertically. We can do a very similar thing with this sort of model. So we have the center point. We just need to know what is the normal of each one of these faces to be able to move them in the specific direction. So we can come in here and say the surface closest point. Now, it's already on that surface, but if we use the surface closest point, it'll give us a UV parameter of that surface, which is helpful later on. So we'll use these center points as the points. And we'll use this surface as the surface. Now, if we are to evaluate that surface, with that UV parameter, we get extra information out of it. We get the normal, we get the U and V, we get a frame that you can kind of see that it made a frame. Now, you can see that some of those points weren't directly on that surface because they're sort of spanning between points of the surface. So as you increase that curvature, they sort of come off of it. But we'll use those normals to sort of generate these sort of triangular pyramids. So if we have this normal, they should be pointing either out or in, depending on which direction we're going. And so we can move these points by these normals, and it'll sort of pop them out in that direction, right? Well, if we want to make some sort of triangular mesh from that, we could go through in a very tedious way. We have the corner points here, and we have this point right here. If I deconstruct this B rep for these panels, it'll give me these corner points now. So I have the faces, I have the edges, and I have the vertices. So, I could go through in the same way that we made the triangular mesh for all of these, but that would be extremely tedious, right? But one thing we have is, if you look at these vertices, we have a separate tree for each, or a separate branch for each face with the 3 points. And we also have a plane. So we could use a delane mesh along that plane to generate the right sort of topology for these pyramids. So we just need to merge those together. So we can merge these points and these vertices. And you can see we're already messing up the topology, right? We have a tree coming into a single list. So we need to adjust this by grafting it so that each center point aligns with each face. So now we have 4 points in each list, which is what we want. Okay, so if we use these points in the delane mesh, and we use the frames here, then we should be able to create a proper mesh. Now, you'll notice that we're messing that up again, right? The topology of that has a tree and a plane. So that's actually making 24,000 mesh faces. Is not what we want. So we need to bring these back together. We want a plane for each face, so this also needs to graph. Right? Let's turn off some of this stuff in the back so we can see what's going on. Okay, so we have a simple sort of mesh face built on this surface geometry, made with standard tools that create that mesh for us. So it's a very complex mesh made using the logic of delane mesh. So that's really useful. If we can take geometry and transfer it into mesh geometry, one, it becomes easier to use for the computer to handle. And if we can generate the mesh topology with clean sort of polygons, then that helps us down the road. Okay. So we can take any sort of surface and make, we can create meshes based on that UV surface, right? You know, this is similar to what Lunchbox is doing with that triangular surface. It was using the UV coordinates of that surface to make this mesh. So if we do that without Lunchbox, I mean, we can do it with Lunchbox pretty easy as well. But if we do that without Lunchbox, we can see a little bit of how that works. So I'm going to use the same sort of surface. Let's group these things so you can see what's what. Does anybody have any questions while I'm doing this? Okay, so we have this surface, and if we want to turn it into, say, a quad mesh, preview. Well, there's a lot of tools that are available under utilities. You can see where to go? Mesh surface, which creates a surface UV mesh. So this works a lot like Lunchbox. You can determine how many faces you want in each direction, and it'll divide up that U and V domain to create that mesh. Now this looks pretty smooth. You can see this topology. If I were to turn off that the mesh preview edges, it looks like a smooth sort of surface, right? And that's only because I've set so many polygons to represent that mesh. If I come down, let's see, I think there's some settings, flat shade, maybe. Let's turn these off again and see if that helps. Not really. Let me put a custom preview on it so it's a little easier to see. If I give this a gray color, you can see it's not transparent anymore. You can see the individual quads of this. Now that is the geometry of this mesh. When I turn this flat shade off, it doesn't make it smoother. It's just applying some color to this mesh to make it appear smooth, and it's sort of blending those across that surface. Okay. So flat shading will show the individual segmentation of that. It's a little easier to see what that mesh is doing. Otherwise, it looks a lot like a surface. So let's see if there's examples that we can clean a mesh. And so there's some actually new tools that are available in I can't remember if it's if Rhino 6 has this or just Rhino 7. But there's a tool called Quad Remesh, which is amazing. It works really great. And so mesh topology in general has a dramatic effect on many things, from visualization to simulation to analysis. If you have a really weird sort of mesh topology, it just won't look right because it's going through and it's calculating all the normals, the face normals and the vertex normals, and using that to create smooth shading across that surface. So if you have weird long edges or odd discontinuous normals, then it's gonna look even more faceted than it needs to be. And if you're using a mesh for some sort of analysis, structural simulation, sort of form finding, the topology has a lot to do with how these things sort of move and stretch and work structurally. And so you want as clean of a mesh as possible. And ideally you want a mesh that has pretty consistent size and shape to all of its units, right? So in this case, I tried to get a surface. I cut that surface with another another line just to make a trim surface as well, and that just makes it even more an even more complex surface to try to mesh, right? When we have this surface UV parameter, oh, I didn't save that. Well, let's cut it. Okay, so I'm going to look at this in top mode. I'm just going to draw some sort of shape there. And I'm gonna bake this mesh, or sorry, bake the surface just so I have a surface that I can project that onto. Sorry, I didn't internalize this other surface for you, but we can make it pretty easily. Project this curve onto the surface. Is that, and I'm going to trim this surface. Okay, so I have this surface. I'm going to bring it in. Single surface. Now, if I were to just turn this into a direct mesh, which is another way we can convert things to meshes, this gives me some capabilities to adjust certain settings. This would essentially be the same as if I selected that in Rhino and said mesh, and a little dialog box would pop up with some sort of controls. So I can look at more detailed controls and have some control over maximum angles and things like that. I think that's a really unintuitive way of making a mesh, whatever those things sort of mean. So I don't typically do it that way. But if I use this, you can see that it's kind of making this mesh, and it's kind of dirty. It's not consistent sort of sizes of the grid. You have mix of triangular and rectilinear mesh faces because it's clipped on the outside. It has all of these weird sort of edge conditions where it's trying to make those fit better. So that's really not the topology we want, especially if we wanted to use that for some sort of simulation or control geometry for some other sort of structure. But the quad remesh is really great because it'll take whatever whatever topology you have, and it'll basically redo it for you and try to make it as consistent as possible. So if I turn this off, you can see now like we have roughly the same size quads. Let's see if I can get this. More visible for you. You see, have roughly the same size quads. The lines are relatively smooth and continuous. You have these little nodes where the topology is sort of like, changing direction because it's not a consistent like UV sort of pattern anymore. It's trying to match the edge sort of condition a little better. You can also supply it some other sort of like surface or line across that. So let's see if I were to actually know what this is going to do. Let's see if we can turn the surface back on. I projected this line onto here, and I wanted to somehow use that to guide the way this remesh is happening. Let's hope this works. It should use that as a template and kind of try to match it. You can see it does a fairly good job. Lines are now sort of flowing in this direction, and so you can use that to help sort of determine if I put one across this way, I bet these would all start to align more with that one as well, and you would get this sort of somewhat quad facing in that direction. So that's a great sort of tool. It takes like a really jaggedy looking mesh and simplifies it quite a bit, and that's I think just in the newer versions is that working. Does anybody with Rhino 6 see that? I know it's not in Rhino 5. It's not in Rhino 6. Okay, so it's just going to be in the work in progress then, but it's a really great sort of tool if you need it to do something like that. Okay. Okay, and there's other ways of cleaning up a mesh, and it's through subdivision, and that actually works really well. So subdivision is sort of a method that'll take whatever sort of simple topology of a mesh and subdivide each face, and in doing so, it makes it slightly smoother. So that's kind of great because it'll also take jaggedy sort of forms of meshes and iteratively smooth them out by adding more faces and adjusting the vertice locations. So there's a couple of sort of algorithms for that. We talked a little bit about Catmull-Clark subdivision, sort of working with Pixar, didn't we? think we did that. There's also another guy named Loop. So even though it sounds more like you're iterating through and looping through something, his name was Loop, and it's subdivision. And so these are slightly different. So the Catmull Clark will take whatever sort of face and subdivide it and get new quads. And the Loop will take whatever sort of face and subdivide it and get triangles. So they're slightly different, but they work pretty well. So let's quickly do that, and then hopefully we have some time to move into our studio sessions. Okay, so I'm gonna hide this real quick. I'm gonna make a simple sort of mesh cube. Not curved geometry at all. And I'm gonna give it one face per side. Okay. Now, if we use our Weaverbird subdivision tab, you can see there's a lot of other ones. The two that we'll mainly focus on is Loop and Catmull Clark. Let's look at Catmull Clark. And so it'll take that, and you can see, the object that it makes inside is somehow smoother. It's not really building from the same sort of vertices anymore. And it's also got a lot more faces. So that's just one iteration. So I think we can go up to like 3 and it'd still be happy. You can see we almost have a sphere, right? If I let's preview this a little bit. So you can still even kind of see the corner points where this one is divided more, this triangular face, you have these 3 quads. So as it's smooth, it's more and more faces are added, but it's also smoothed out, so there's no corner points. So that's really useful at creating continuous curvature in a mesh, right? Where a surface would naturally sort of have that. If you wanted to move each vertex to try to get it to be smooth, it would be very difficult. But through these smoothing algorithms, we can start to do that. And we can also determine how we want it to treat our naked edges, which is why it's important to know if we have a naked edge or not. In this case, we didn't have any sort of naked edges, so it's going to be smooth everywhere. But if we did have a surface that wasn't fully closed, the edge condition could either be fixed, and all the smoothing would happen in the middle, or the edge can get smoothed as well, and so it'll tend to be more curvilinear after that as well. If we look at the Weaverbird loop subdivision, you'll see similar things happening. It's slightly different, so the form is actually slightly different. The Catmull Clark has all quads, and this one we have all triangular faces. You see how that works with one iteration. And with more. Now, because it's creating this sort of triangular subdivision where the first iteration, cuts that square into triangles. If I set this to 0, I think you can see that. It cuts this triangle, this triangle, this triangle, and that triangle. Through iterative subdivision of that, you still get a couple of these triangles, sort of showing up. It's not a complete sphere anymore, but it's smooth sort of geometry. So these do different things, but they're both these sort of smoothing algorithms. Okay, so those are sort of the basics of sort of mesh topology, creation, smoothing. Let's see if we can apply it more specifically to a situation. So I'm going to turn these off real quick. So for one of your assignments, you're going to be doing this to your computational facade that you made. So if I'm not going to go over it, but I'm going to show what you'll be doing. So I've basically taken the geometry that we ended up with from the previous class, which is this this sort of thing, right? We had the frame system, and we had the sort of glass or flat panel that was in there. If we just treat this as all one sort of system, and we wanted to convert that into a mesh, well, the frame sort of system is all sort of planar, or not planar, but quad type elements. So we can split that up using a deconstruct and make a mesh out of that with single mesh faces in the U and V direction. So that's a pretty simple conversion. Now the other one on the bottom was not a quad or a triangle. It was actually it was a planar surface, but it had six points. So we'd have to figure out a way of converting that into a mesh. We could somehow divide a line down the middle, and you would have two quads. We can get a point in the center. There's a couple ways of doing it. Weaverbird has another tool called a Weaverbird's tile that helps with that. If we take the edge lines and join them together, then we get one sort of polyline for the whole thing. And then it gives us different ways of making a mesh out of that. So if you scroll over here, it says the filling strategy. Well, we can skip it altogether, which makes an invalid mesh, because there's no sort of subdivision of that, and it can't make it out of 6 points. You can scroll through these and see what the strategies would do. This one sort of subdivides it in half into two quads. There's another one that sort of puts a point in the middle and draws triangles to it. These are all ones that you could easily do. You can make a script for any of these. This tool is also available that allows you to do that. This one just picks one of the nodes on the edge and draws triangles from the other ones. All good strategies. This one sort of zigzags back and forth. It makes long triangles, which is maybe not the best for this geometry. The other one was available. Also cutting across. This one I kind of like. It divides it into three, and those are relatively even quads as well. Maybe I'll just keep it with that one. Okay, and so once I have those, I also have this tree branch that can merge together. And I'll end up with a bunch of meshes that are all quads or triangles. I think they're all quads in this case. Now, if I want to stitch those back together, if I were to smooth out all these and subdivide them, each individual face right now is a single mesh. So like the smoothing between those would not really happen. I want to create a single mesh from that so that smoothing works. And so I'll need to join the mesh together and what's called welding. So right now, each corner point is not a single vertice that's shared with all of these. Each one has a duplicate vertice on top of itself for this face and for the other faces that are using that. So meshes, unlike surfaces, you can have meshes that have faces that are not touching. If they're joined together, it still considers it one mesh, which is kind of interesting. So they don't have to have shared vertices for them to join together. So that means that that vertice list is only drawing the mesh faces where those vertices are, and if you happen to have two of those vertices overlapping, it doesn't naturally combine them. So tools like this, you have mesh join is another one that will join them together. This does not weld the meshes, it just joins them together into one mesh, which is something we can do, and you'll see that sort of updates into an invalid mesh, which is unfortunate. If we use Weaverbird's tool for joining and unifying, we do get a single sort of mesh that has 774 vertices and also 744 faces. Now there's a lot of tools that I'll usually, if I'm having trouble, the mesh isn't working. There's various sort of weld meshes, weld vertices that are all typically in some of these tools up here for fixing mesh topology, basically. So flipping a mesh, welding a mesh, unifying a mesh is another one. How I mentioned if we had one sort of clockwise and counterclockwise face, their normals would be pointing in opposite directions. So these mesh faces down here, if I were to go through and not put this in, I will just join them together and see what it comes up with. And I'm going to do some sort of smoothing to see how this creates some sort of continuous geometry. Let's hide this stuff. Now that looks pretty good. Like, it's fairly smooth. You can see the topology is pretty clean across all of these things. But there's this dark line around here. And what that tells me is that the computer doesn't know how to shade this smoothly because the surfaces in here were facing the opposite direction. So you can use that to your advantage and have that read as this sort of like little Oculus type thing in there. But if you want them to be consistent, you might unify the mesh before you subdivide it. And so then that'll smooth that out. Now the geometry itself is not changing, it's just the direction that those vertices are stored are flipping around. And so that the computer can now display that with more curvature. Right? So one of your assignments is going to take whatever sort of facade you made and generate a smoother version of that. See if you can work with the subdivision algorithms. And if things are not working, you might want to do things like joining the meshes, welding the meshes, unifying the meshes to get some connected curvature happening. Okay. Let's look at one more example. I'm going to see if I can. I'll use this surface again. Let's use this one up here. I want to see how well I can control this subdivision. Okay, so with this, I'm going to start out by using, I'm going to use a diamond pattern. And I'm gonna do a very similar version to what I was doing before with the quad, where I'm making these panels on the surface and raising up, or I think I used a triangle before, making the panels on the surface, raising up the middle to create some sort of pyramid-like structure. But I want to adjust how that happens. So what this gives me, it gives me the diamonds in the middle and also the triangle on the outside. So I have two different types of surfaces to deal with. I'm going to get the area so that I have these center points. And this is just from the diamonds. I'm going to use that surface closest point like I was doing before. I have this surface, I have these points. And I'm going to evaluate this surface to get that normal direction. Evaluate the surface. And get the UV direction. So that gives me the normals and the frames. Now, so far, this is exactly what I was doing before. Now, I want to move that center point up to be able to create that pyramid. I'll give myself some space. I'm really close to this other scripts. And to do that, I want to use an image mapper to help me out a little bit. Or an image sampler, sorry. So I'm going to take this UV position and I want to add an image. And I'm just going to go grab one from last week, I think. So I'm going to grab the one that has the center sort of gradient. Find it. Okay, center gradient. And I want to set it to look at the brightness. So it gives me one sort of value for that. Now the other thing, if you remember, is I want to use a simple sort of parameterization of that surface so that this is sort of mapping from 0 to 1, 0 to 1 across this surface instead of like being down in the corner by some other sort of parameterization. Okay, so I have this. This is going to give me some sort of value coming out at each point that I've selected. And I basically want to multiply that by the normal. So I'm going to multiply. I'm going to use that as some sort of scale. So the ones in the middle should move more than the ones on the outside because of this. And I'll also give it I'll give it an extra point to multiply, so I can just like scale it up how I want. So I'll give it a slider just as a scalar. So from there I can move that point. Move that amount, and you'll see the ones in the middle are slightly higher than the ones on the outside. You can't really visualize that very well, but we'll do that. So we have that. So we also need just like before, if we wanted to use a Delaunay mesh, we're gonna get the edges, or sorry, the vertices of each one of these. So I can deconstruct the B-rep. This. I can merge these two together. So what I have right now is a tree structure right here. So I'll probably want a tree structure on this one, so I'm going to graft it. Go in a mesh and use this frame. So if I turn off some of this other stuff, you should see. Oh, there's another thing I did. So let's go back to that. Did the same thing that I did before, that each one of these is in a list. So if I graph them, then I have a better sort of organization of data. So it's only making one instead of okay. So you can't quite tell what's going on. Let me add a custom preview. So you can see that these are higher than these are over here. So it's kind of like a pattern that's fading off. And that's great, but we still have these pretty angular facets to the surface. So I want to smooth that out. And I also want to add these triangles back in there. So I'm gonna come back here to where these triangles are, and I'm gonna add a simple surface. Simple mesh. Since they're triangles, that can convert pretty easily into that. and I want to I want to merge that together with this mesh as well. So merge this, merge this. Need to make that the same sort of pattern. And I'm going to flatten these coming out of here into one giant list of mesh faces that I can join together. Let's use the Weaver Bird version of it. So we can join and weld together at the same time. I have one mesh. I can smooth that. And turn off some of the other stuff. And I'm going to look at it in something that renders a little better than this. Let's see if we can turn up our subdivisions. I want to do it 3 times. And you can see that it's also making these edges curl a little bit because I'm not fixing that edge. So if I put a 0 down here, it should fix that edge and sort of not smooth out the corners. So this is, you can see that it's fading off here and it's more prominent there. I can kind of adjust how much that's happening. But we get some nice curved sort of geometry happening because they're all joined together. There's not a seam there, but that's continuous. So this is something you can also do in terms of your facade system to help smooth it out. Is follow these sort of ways of working as well. Does anybody have any questions? No questions? You guys still there? Great. Okay, well,